is about the pointers and objects in C. And the presenter is Kaivan Memarian.
C, and this is John.
About to get on.
Can you hear me now? Okay, so this is John, work with various people in Cambridge, SRI, and University of Kent. So C, it's a language we don't really like to think of when we are semanticists because it's pretty large and, let's face it, pretty ugly. But there have been lots of epic work in the last few years to try to model C. And in Cambridge, we wanted to do the same, but we have an interest which is quite different from previous work, which is that we want to model C in the way it's used in practice, not really the way it's been defined. So to give you some context, we've been making a formal model of C, which we call Cerberus, which models a significant fragment of the C11 language. So we start from the ISO C11 definition, which is the normative definition of the language. And for most of the language, the standard is pretty clear and does match practice. So we start from that. But for the question of memory model and what a pointer is, which is what we're interested in, the standard doesn't really either say much or does not correspond to practice. So we need to come up with something that doesn't exist. Our model is an executable semantics, which means that we have a test oracle, which allows you to look at reasonably small program and explore all the possible behaviors. Because we're interested in memory model issues, we've designed the semantics to separate the semantics of expression and statement from memory model so that we can focus on that in isolation. So our semantics is done by Elaboration, which means that we take a C program and we translate it into a simpler language, a core language that we design specifically for the purpose of making explicit all the subtleties of the dynamics of C. And then our semantics is really just a pair of that elaboration function and an operational semantic for core, which is a more traditional language, joined with a specific memory model. To give you an idea of what this looks like, on the left of the slide, you have a picture of the C standard. And this is the part of the standard which explains the dynamics and statics of a particular binary integer operation, which is the left shift. On the right side of the slide, you have a snapshot of our elaboration function. So the big expression at the top is the C expression we want to translate. And if you want to explain everything that that expression will do, you need to make a core program which is quite a bit bigger than the original C source. So the thing this program does is, for example, implicit type conversions, describing the loose ordering that is part of the C semantics, detecting all the possible undefined behaviors because there are cases where this expression can fail. When we create that core program from a source C program, we don't make any prior assumption about what the memory model is. Everything that has to do with memory model and pointer is completely separated. Instead, if you look at this C program, for example, when we turn it into core, all the interactions with the memory model are restricted to a very small and opaque memory API that we can define and explain in another part of the semantics. So now that I've given you the context, I can start talking about pointers and memory model. So pointers in C. When you think about pointers, you can take two rather extremely opposed views of pointers. Either you can think of pointers as being a completely abstract construct because they seem to be quite isolated from the rest of the language. You can only do a very restricted set of operations on pointers, very simple arithmetic. You cannot really mix pointers and integers, for example. You have cast, but they're very limited. So you can think of them as being abstract, and it's nice and high level. On the other hand, you can take a very concrete view of pointers, which tend to be the point of view that programmers have, which is that they are just numerical addresses. And if you do take that point of view, the state of the memory becomes a finite map from these addresses to bytes. So you've lost some level of abstraction if you do that, but it's simple and it sort of matches the way pointers are implemented in the underlying hardware. Unfortunately, C is neither of these views. So first, even so pointers seem to be isolated from the rest of the language, C still provides you with ways of casting integers to pointers and back, and people do use these in practice in ways which are in fact more perverse than what the standards actually allow, but if real programs do need them. Also in C, it's a low-level language, so you are always allowed to look at the representation of any type, in particular, including pointer types. So you can look at the bytes, modify them, and somehow you've changed the pointer. So abstract view doesn't work. Unfortunately, the concrete view doesn't work either because over time, compilers started becoming more and more powerful and in particular more and more aggressive in the optimization they do, in particular for the alias analysis optimization. And I'm going to show you this with a small program. So let's have a look at, this is a small program, and by the way, we're not saying that this is the kind of program you should be writing, and nobody writes that. It's just a pathological example, just to make a semantic point. So let's have a look. This is the graphical representation of the memory after the initialization, the allocation in this program. You have two integers, x and y, which are here, and you're going to make two pointers to these objects. So first, you have a pointer p which first takes the address of x, but then you're going to do some arithmetic, and here we're interested in one particular execution of that program where the allocator happened to have allocated y just after x. So if you do that +1, you probably get a pointer that points to y. At least it looks like it from the address. And the q pointer is just created by taking the address of y, so there has to be an honest pointer to y. Now you're going to do some guard, which is going to check that the memory representation of both pointers is exactly the same. That's what the memcompare does. And if these two pointers have the same address, you're going to try to do a store through the funky pointer p that we try to make to y. Now, if you take the concrete view of pointers, you would think that after this store, if we do indeed get into the then branch, if you load from x, it's still going to be 1. If you load from y, it should see 11, the access you've just done. If you load through p and through q, you should see 11. Unfortunately, if you run this program on GCC with some optimization flag set, you see something quite strange. When you read from x and y, you still see the initial state of the memory. When you reread through the p pointer, you see the access you thought you just did. But if you read it through q, you don't see it. So a priori, it looks like the alias analysis, because this is the part of the compiler which produced that funky behavior, for some reason assume that p cannot alias with y or cannot alias with q because of the way we've created that pointer. You could think that this is maybe just a bug on GCC, but in fact, a few years back, somebody asked a very similar question to WG14, which is the ISO committee in charge of writing the system that is maintaining it. And they gave an answer where they said that implementations, so compilers, are allowed to track the origin of bit pattern. And so origin here is what we call provenance. And in particular, when you have two pointers with the same physical representation but different origin, provenance, they're allowed to consider them to be distinct. And so this was an answer they gave in 2004, so quite a while back. In the meantime, a new version of the C standard came up, C11, the one we use in our semantic, but they didn't add any wording to explain what that single sentence means, because even so this sentence is hitting at the existence of provenance, it's really not saying anything. So compiler writer used that sentence to license them to keep on writing this nice optimization, which make your program go faster, but to be able to reason about the soundness of their alias analysis, you need to know what provenance are. So here is a slide where I give you a basic idea of what provenance are. Since we are semanticists, we don't care about how pointers are implemented, and provenance have nothing to do with implementation. You're not going to change, you're not going to carry them in the actual implementation. It's just something at the high-level abstract C machine. So at allocation time, you're going to make a fresh allocation ID. And now a pointer is going to be a pair of a provenance and an address, like before. A provenance can either be empty, doesn't correspond to any allocation, or associated to a particular allocation ID. But now that we've changed what pointers are, of course, we're going to have to update the semantics of all the operations we're allowed to do on pointers, in particular arithmetic. And morally, what they're going to have to do is preserve provenance of pointers. The place where provenance actually do something is for the semantics of doing a memory access when you use the indirection operator. When you try to do an access through a pointer, what you're going to do is take the address, which gives you a place in the memory, look at the provenance of your pointer. You want to have a provenance which is associated to an allocation. Since an allocation refers to an object in the memory, it corresponds to a footprint in the memory, and what you're going to do is just make sure that the address is within that footprint. If it's not, your access is undefined behavior. So let's go back to the program we were looking at earlier. This is still the picture of the memory state, but you will notice that now every object has some allocation ID that was created at allocation time. When you create P, it takes the allocation of X, so allocation 0, and the address is that of X. But after doing the increment, the +1, the address has changed, but the provenance hasn't. So this is the address is not within the footprint anymore, so the pointer wouldn't be valid to the access. On the other hand, Q has the provenance of Y, and it's within the footprint, so it's valid. And this is what makes this access undefined behavior, and therefore the whole program undefined behavior, and the behavior we observed GCC do is therefore allowed. It's okay for the optimization to do that. Okay, now that we've added new behavior to pointers, we need to see how this interacts with all the low-level practice that people do when they write system codes. So what kind of thing can they do when they write system codes? They can cast pointers to integers, do some arithmetic on these integers, and then bring it back to a pointer. And this is very useful in practice if you want to store metadata on pointers, because you know that your pointer needs to be aligned based on its type, so you will often have bits that you don't really use for the address, so you can store metadata when you write a garbage collector, for example. You can manipulate the representation of byte. You can maybe transfer pointers over I/O, and also if you happen to be writing embedded code, you're going to create sometimes pointers just from constants, because you know what's in that specific place of the memory. So to be able to deal with all these users, we present two proposed semantics involving provenance. In the first one, since all these practices morally all involve having some interaction between pointers and integers, the first proposal just not only have provenance on pointers, but also carry the provenance through integer computations. So when you cast a pointer to an integer, the integer ends up also having the provenance. So this is quite heavy, because now even our integers are not just integers, they are pair, and you need to update all the semantics of all the operations to somehow do the same stable thing for this provenance. So this is quite heavy. So we also have another simpler semantics where we do not track provenance on integers at all, but instead when you're going to cast integers to pointers, you're going to take the address that you would get from that cast, look into the memory to see what live object there is in the state, and somehow retrieve a provenance to, if you can, to make a valid pointer. And of course, you have various choices in the semantics to restrict which object you're allowed to retrieve pointers from. Now, both of these proposals have pros and cons. The obvious con of the first one is that it's making integers much more complicated, and in particular, it restricts what integer optimization you're allowed to do. You're breaking algebraic laws about integers. But for P and VI, you could think that this might be very restrictive for the alias analysis, because since we're not tracking provenance in the integer world, a priori alias analysis cannot do anything as soon as you cast things to integers. And you may think that you could write a C program where you just put a constant which somehow guess the address of an object. And if you do that, this is very bad for the alias analysis, because the alias analysis need to be very conservative and cannot do as much optimization. But luckily for us, since the allocation is non-deterministic, you can't really do that. It's not possible. So we discussed this in the paper, and we discussed we compared the both proposal with classic optimizations and see what's allowed and what's not. Okay, now that we have proposals, we need to somehow validate it. Here, it's not just a practice of taking an existing standard and turning it turning it into math, because there is no clear agreement between practitioners on what the semantics of pointers should be. So what can we do? Well, we can look at the millions of lines of code of C code that exist out there, because in fact, this is somehow defining a de facto standard, because people use it in practice. So when the semantic of the language should allow this program to keep on running. So with colleagues in Cambridge, which work on the CHERI architecture that Alistair mentioned earlier, which is an experimental ISA which provide hardware capabilities, which you can think of capabilities as being runtime provenance. We can use their tool chain to collect experimental data. So for example, they've ported FreeBSD to their architecture. So they had to change FreeBSD to be compatible with a provenance semantics. So just by looking at the changes they had to do, but also just by knowing that the fact that they managed to port FreeBSD and get it to boot means that this semantics is not too restrictive for operating system. We also wrote a dynamic analysis tool which implement checks for our provenance semantic and run them in some benchmark from SPEC CPU 2006, and we managed to get it to run. So it's not, for real C code, it doesn't seem to be too restrictive. Another thing we can do to try to validate our semantic is to go talk to people who write compilers and ask them, is it going to make your compiler generate poor code, or is it going to be implementable? So that's what we've been doing over the past few years. We've been attending to a compiler conference, talking to compiler people, and the general consensus seems to be that while this may require them to change some optimization, maybe turn off some optimization, it seems to be implementable. So with this knowledge, we can now go back to the WG14 committee, the people writing the C standard, and try to get them to, based on these two models, come up with some wording that could be part of the next iteration of the C language to make the earlier sentence into something more detailed that now programmers and compiler implemented can all agree on. Okay, so back to Cerberus. These two models, we've implemented them on top of our Cerberus semantics so that now we can run small tests and play with it to further validate it. Since the kind of tests we want to run are like not very clean, nice fragments of C, we had to make the semantics more involved. So we did some reengineering, and now we can start running realistic programs like, for example, BZ2 or some FreeBSD utilities. Also, since we want people who not necessarily semanticists, but just compiler people to use our tool, we've made a web interface so that it's pretty easy, accessible for anyone to use. So this is what it looks like. You can write a small C program. It translates into core. You can relate the two programs if you want to see what's happening. You can relate the generated core program. It explains to you which part of the standard was used to generate that program. You can get a picture of the memory, and you can step through, get all the behaviors, find the undefined behaviors, and such. So to conclude, pointers in C, everyone seems to be using them, but there still isn't really a clear consensus on what they are. And in this work, we've been trying to come up with a proposal for specifying what they are, what alias analyses are allowed to do, and we've implemented it into an executable semantics so that people can use it as a test protocol, and now we are aiming at getting some normative wording in maybe a next iteration of the C standards. You can access the web interface of the tool I just showed you at this address. Thank you for listening.
Question from Slido. Are the optimizations allowed by the Provenance really worth it performance-wise in practice?
Based on compiler people, if you remove Provenance, it's like going back to 0. So yes.
All right. Can you shout? Right, can you shout? All right.
So you said that you're using non-determinism to argue that pointer addresses can be guessed. Now, given that memory is observably finite in C, how do you make that argument when memory is so full that the allocator basically has only one choice?
So the argument we make is that even so the memory is finite, you could just reorder some objects. So like you will always find a new address where by just shuffling objects, even if they are completely densely occupying the whole memory, you can't write just a program that works for all these orders. Okay.
All right. Anonymous asking, how does this work compare to the work formalizing C semantics in the K framework?
So in the K framework, they were really following the C standards. So many of the things that people do in practice are sometimes clearly made said to be undefined behavior by the C standards. For example, you cannot do arithmetic that take a pointer outside of the bound of an object. But in the experimental data that we collected, for example, when you run the test suite of FreeBSD, for example, you get a few 100,000 occurrences of such pointers just when you run BASIC, for example. So according to the C standards, just booting your machine is undefined behavior. So we're trying to go beyond what the standards specify.
Thank you. Derek.
Hi, yeah. So there's some closely related work that appeared at UPSLA last year on this twin-allocation semantics by Lee et al. I know you compare against this in the paper in detail. I was just wondering if you can give a high-level summary of how that's related, because they're looking at something very closely related in the context of LLVM.
So in the paper we compare what we think would be a translation of the LLVM semantics to a C level, because you don't have the same constraint. So I think we showed that they are neither an inclusion of each other, but we seem to be allowed. The only way we can compare them is by looking at which optimization they allow, and they seem to both be allowing the same optimizations.
All right. So time for lunch, but let's first thank the speaker again.